Look at is fuel quantity measurement. And so the kind of summary of fuel quantity is shown here. We're going to have parts inside the tanks that are going to be able to display a fuel level. We have to have, most of your newer aircraft are going to have a computer of some kind that's going to control this system. And so what you can see here, there are three, shown on this one, there are 3 tank probes. The probes actually give you level. There's something called a compensator, and we'll look at that, what the purpose of that is. We have to know what's known as the dielectric constant of the fuel, or the dielectric capacity of the fuel. These are capacitance-based systems, and so that's where that term comes from. We have a densitometer. These are going to give us a fuel volume, a fuel level, but on transport aircraft, we want to know the fuel in pounds, and so we have to convert, these systems are going to convert a volume in a given space to a weight, or to the total pounds of fuel. And so you got to know the fuel density. And that all feeds into in this case, they call it fuel quantity indicating system processing unit, which is a fancy name for fuel computer, which is what we always just called these, even though they have that name. Why do we do pounds? Why are transport aircraft in pounds rather than gallons? Volume changes with what? Volume changes with temperature. What does that mean? In a given volume of fuel, why is that important? So it changes a little bit. What's the big deal? As long as you got fuel, right? So if the volume gets bigger, you have more fuel. Volume gets less, you have less fuel. We do. The volume changes, but if it goes down to 0, you just know you're going to run out, right? Okay. So the reason we have to do it in pounds is the energy content. What we're worried about with fuel is energy content. Fuel is a energy storage. Dead dinosaurs been compressed down into a liquid, probably more plants, dead plant material compressed down into a liquid, contains a certain amount of energy in a given per pound. If we do it in gallons, we don't know, or volume, we don't know the energy content per gallon at a given time, because the energy content is based on the number of molecules. Each molecule has a certain energy content. If those molecules are closer together, more dense, you've got more energy in a given volume. If they're further apart, less dense, you have less energy in a given volume. But those same number of molecules is going to weigh the same no matter if it's more densely packed or if it's more spread out, if you take the same number of fuel molecules. And so that's why on small airplanes, it's not such a big deal. You don't have a ton of fuel. That little bit of expansion contraction is not going to make a big difference. Large airplanes carrying a lot of fuel, that effect is magnified. And so that's why we have to convert it, why we convert it to pounds, to know how much energy. So if we look at a simplified version of this, what we have, that fuel tank probe, what symbol is that? What is the fuel tank probe, basically? Looking at electrical here, electrical 1. That's a capacitor. It's a capacitance-based system. And we run a AC current. See, it's handy having AC on the airplane. We run an AC current across that capacitor. It's going to have a certain capacitance. Okay? And then we have a reference capacitor that this indicator, it can kind of compare the current flow on one side to the current flow on the other side here, from the reference to the fuel tank probe. Now, how does that capacitor up there give us a fuel level? Resistance? Not resistance. It's a capacitor, so we're dealing with capacitance. We can look at different fuel levels if something changes. What's going to change How is this going to change as fuel is used? What's going to happen? What is that fuel serving as right now in that capacitor? That's the dielectric. Okay, the fuel is the dielectric in the fuel tank probe is basically a capacitor. The fuel serves as a dielectric. And what happens if we change the amount of dielectric between those two plates? It changes the capacitance. So that's how these systems work, is they sense the capacitance in the probes, and that capacitance changes as the fuel level changes in order to, and then we have an indicator that compares that to a known capacitance in order to give us a fuel level reading. Now, this is purely going to be a volumetric. Okay, this is a volumetric setup here. Then that indicator or that level would then have to be, we would also need to know the density, and then we can convert it to a volume. Okay. Sorry, to a weight, to a weight. Now, this one is a very simplistic version. What you'd probably see is something more like this. This is what the actual aircraft looks like. Is you're going to have multiple probes, because you're probably going to have probes out by the wingtip and a little bit further inboard and a little bit further inboard and a little bit further inboard. Now, they're all wired in parallel. What happens with capacitors when we wire them in parallel? What do they act like? If I wire a bunch of capacitors in parallel like this, how do they act? What are they doing? Do the capacitances add together? Do they essentially, this plate right here, and this plate here, and this plate here, act like one giant capacitor, spread across multiple points inside the tank. Okay? So when the tank's full, all of these, say this is the wing tip out here, this is the wing root down here. When the tank is full, they've got, every one of them has fuel between the two plates. Okay? And then as the fuel level starts to drop, your dielectric constant, or your dielectric constant in the first capacitor will change, right? That'll change the capacitance across this whole group of them, right? And then as it continues to drop, now another one might start to be out of fuel, and then as it continues to drop, now the inboard one might be out of fuel, right? It's going to come down the inboard one. So your inboard ones tend to be submerged up until, the outboard. And maybe, sometimes the fuel will start to, it'll be getting lower on the outboard one, and then it'll start to come down the inboard one, right? Because these are sloped tanks. And so the engineers, when they design these, they know the volume of the tanks, and they know the geometry of the tanks. And so if you know the density of the fuel, and you know how high that fuel is sitting at each one of those capacitors, and how big that tank is, you can convert that to pounds of fuel. And that's what our fuel quantity indicating system is doing. And so that's where you've got these other things. So that reference capacitor is in the same tank, because different fuels are going to have slightly different dielectric constants. Jet A versus Jet A1 versus Jet B versus JP8 versus, you got all these different fuels. And then whether the fuel contains Prist or doesn't contain Prist. What does Prist do? Anyone know? Anyone ever heard that term before? Okay. This time of year, we get what's called Prist positive fuel. During the summer, we get Prist negative fuel. What do you think Prist does? It's an anti-icing agent. Okay, that changes the dielectric constant. So wintertime, planes will get fuel with Prist added to it as an anti-icing agent. It prevents water that's in the fuel from freezing. But you don't need it in the summer, and it costs extra, so why put it in that time? So this reference capacitor is in typically one of the lowest points of the tank, and that reference capacitor is also known as a compensator. It compensates for changes in dielectric constant. Remember I talked about the compensator wash line when we were fueling? That's directed at this reference capacitor, this compensator. Reference capacitor, compensator are the same thing. These ones, fuel washes off of them, fuel gets on them, fuel washes off of them, fuel gets on them. So it's gonna constantly be kind of washing the level sending capacitor. It's gonna be kind of cleaning those plates as the fuel goes up and down. But this reference capacitor, this compensator, oftentimes will never, except for when maintenance dumps the tanks, needs them totally empty in order to go in for maintenance. Rarely will it be in open air. The whole point is we want it to be fully submerged in fuel all the time. And so that compensator wash line is going to spray fuel across it to knock crud off of those plates so that they can give an accurate reading. Okay? And then you can see I've also added a densitometer here that can tell us how dense our fuel is in order to complete that calculation to figure out pounds rather than just volume. Okay. If we look at a wing that has these, you can see we've got a bunch of different things. So tank unit on the legend here, tank unit is the fuel tank, or the capacitance-based fuel tank probes. So you can see here, and this is that 2-tank airplane, there are 13 tank units on this airplane. So you've got essentially 13 probes that are all wired in parallel that create one averaging giant capacitor in the wing. Okay. Now, the inboard most one, number 1 here, at the base of it, it also has the compensator on it. It has that reference capacitor. So the inboard one actually has two. It's got a long capacitor tank probe that sticks up, and then it's got a little short squat one at the bottom that's always going to be at the low point of the fuel. Okay. There is a low level sensor here, so if fuel gets down there and gets low, that's not good. Okay. And then we've got a fuel temperature sensor here. Now this plane doesn't show the densitometer here, but there's a densitometer in the right wing. Okay. The other thing we've got are magnetic level indicators, and you can see those little triangles, 1, 2, 3. And those are like the drip sticks that you did during lab. The 727 has drip sticks. These have magnetic float type ones. So when you pull down on them, they don't drip everywhere, and we'll look at how those work as well. So those are part of the manual. If the electronic fuel quantity system doesn't work, you can use these magnetic level indicators in order to calculate a quantity. But again, not an ideal situation, takes a long time, prone to human error. So again, our planes had it, we could use it, we tried not to. So here's what one of these quantity indicators or quantity sensors looks like. Capacitance type fuel quantity probe. It's essentially, they're cylindrical, and they've got your outer plate, you can see it's got holes in it to allow fuel to go in. They're open at the bottom. Fuel can flow up and down from the bottom as well. And then you got your inner plate, and those act as your 2 plates for your capacitor. This one too, most of them then have a third plate kind of on the outside. They've got a shell around the outside. So that's what they call the still tube right here. And that helps to prevent fuel that's sloshing around from sloshing on it and everything else. It prevents it from getting, these plates are pretty thin. If fuel's constantly sloshing, it could dent them or it could damage them. So that still plate, still tube means by still is it keeps the fuel still that's inside of the probe. So it's not sloshing around and banging against the plates, causing, these are thin enough too that if you got fuel sloshing, it could actually cause the plates to like bang together. They're very, very thin. They're like 20,000 sheet metal type stuff. So the fuel will be able to go up and down inside this probe, and that'll change the capacitance of the probe based on dielectric. This is actually sitting upside down. Typically these are installed from the bottom of the wing. Okay. Some are installed from the top, some are submerged, they're submersible. Okay, this is one that's designed to be bolted into a panel. Actually, this one's probably a top panel one. There's a panel on top of the wing you open, and this is sitting just underneath the skin, just below the skin. And then there would be an electrical hookup at the top to tie it into the system. I don't know where this one's from, it's just a diagram. So it could be a top probe, could be a bottom probe. It's not a submersible probe, I can tell you that, because it's got the flange on it. Okay. So here's what some actual ones look like. Now these are the submersible probes I was mentioning. Okay. So here is fuel quantity probes. You can see they don't necessarily have to be installed straight up and down. So rather than, the wing gets thinner and thinner, rather than having 13 different sizes, right? Maybe you have 2 or 3 different sizes. And if you get to a point in the wing where it's a little bit too thin, you can take one of the longer probes and install it slightly sided. That's not going to change how the fuel changes level in there. When they figure out the volume to pounds correction, that's factored in here. Here's the densitometer right here, okay, which is also tied to a probe that's in the right wing. Here's a probe that's sitting straight up and down at the very, near the root, very tall, shorter one out in the wing area. You see there's wiring going to them, it's sealed wiring, very low low current, low voltage. They're designed not to spark. Essentially, it's just reading a capacitance. Inboard, here's one. Here's the tall probe, and then it's hidden by this fuel line a little bit, but the compensator, that reference probe, is down here at the very bottom, staying in the part of the tank that's going to ideally be filled with fuel all the time. So it gives you a reference, it gives you a dielectric constant reference for the fuel to compare the rest of these probes against. And it shows where they all, kind of where they all live here. So you can see B, these probes, there's the 13 different probes and where they are all the way out in the wing. And when you wire it all together, it looks like this. Now, back in the day, all these probes were wired in parallel. The upward one was done to the next one, was done to the next one, was done to the next one, was done to the next one. And then you had two wires that ultimately came in the fuselage and hooked up to the computer. Here, you can see each probe, there's a common wire, there's a common power, essentially. And then you've got a separate wire for each one going back to the fuel conditioning unit or fuel control computer. Why would you go to this version? Why is this on more modern aircraft? Why not just wire them all in parallel? So in this case, yeah, well, if one is screwed up, you can identify it. The planes I worked on where they were all wired in parallel, if we were having a fuel quantity issue on one side, we knew it was on one side. And then we had to go test each probe to try to figure out which probe it was. And they have special test boxes for these that hook up and do capacitance. You don't use a regular meter on them. They have test boxes for them. We've got one over there. But by doing them separate like this on new aircraft, this fuel conditioning unit, fuel control, feeds into ICAS. You can go into the maintenance screen. If you're getting, in fact, it'll do a message, a caution message, if one of these has gone bad. And you can actually defer a single probe. You say, okay, it will still, 13 probes, one of them goes bad. Maybe you're indicating maybe slightly off, but it's still going to be pretty darn accurate if one or two probes goes bad on a given site. And so by having them wired separate like that, it can actually it can say, yeah, that one's, just ignore that one. The computer will actually ignore ones that are an obvious bad. This probe shows full, this probe shows full, this probe shows empty, this probe shows full, this probe shows full. It'll probably ignore number 9 there, right? Or, this is empty, empty, full, empty, 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 empty. It can ignore one or two probes that go bad by having them wired separate. If they're all wired together, you may not even know when one probe has gone bad sometimes, because it'll cause such a subtle throw, or it'll throw off the volume indication subtly, that you may not know it until you do a check. And so these have built-in tests. When these start up, they will actually check each probe and look at the readings from them. It'll compare them across the board and be like, okay, they're all good. Or, well, we got one or two that's bad. And then, but the nice part then from a maintenance standpoint is they can tell you which one's bad. You go into the maintenance data computer, you pull that up in the cockpit, and it says, hey, probe number 9, right-hand wing number 9 is out of tolerance, out of normal reading. That makes it easy to go fix. Well, easy-ish. I mean, you saw they're inside the tank. You got to now drain the tank. You got to sump the fuel. But you might be able to defer it. It may have the ability to fly the plane like that for a period of time until you can get it to a bigger maintenance base or somewhere where maybe they have a probe in stock, that kind of thing. So you have better dispatchability and better reliability as well. Have you guys had RMS yet? No? Okay. That's reliability, maintainability, supportability. And that's where this plays into it. Yeah. The wires are so tiny. I mean, yes, it would, but these wires are you work with avionics more than me, 22 gauge wire, probably. I mean, have you seen a 22 gauge wire or 24 gauge wire? They're tiny, tiny, tiny wires. So they really don't use, again, you don't want much power or current going through them. You don't want them sparking for obvious reasons. And it's negligible, I guess, would be. I mean, nothing on an airplane is negligible. They're going to factor that weight in when they design these. But the gains in dispatchability, reliability, and ease of troubleshooting and maintenance far outweigh the tiny extra bit of fuel that weight is going to require you to carry. Because that's what we weigh. Anything we add to the plane, we weigh how much more fuel is it going to cause it to burn, right? And it's so negligible that it's like, okay, that's paid for by one maintenance event where it takes 20 minutes to troubleshoot it instead of 8 hours to troubleshoot it, right? Here's our densitometer. Well, we got to figure out how dense the fuel is, and that can be that varies based on temperature. It's also type of fuel. Again, is it Jet A, Jet B, Jet A1? Does it have Prist in it? Does not have Prist in it? And so we've got two types. We've got rotational and we've got piezoelectric. Piezoelectric can be broken down into two additional types: torsional or longitudinal. And so in the case of a rotational one, what you essentially have is a little motor spinning a paddle wheel inside the fuel. If anyone has a picture of one, let me know, because they're older, they're hard to find anymore. But if you have a picture of one, I'd love to get one. But they've got a little paddle wheel that basically spins. And the thicker the fluid, the more dense the fluid, the more resistance to spin it's going to have, and the more current that motor that spins it is going to require. Right? So it looks at how much current do I need to spin this little paddle wheel. And they're not super accurate. They're less accurate than our newer ones on the piezoelectric versions, but they're around. Piezoelectric is something where, what is a piezoelectric? If I say piezoelectric, does anyone know what that does? It's a crystal, or it's a crystalline structure that vibrates at a frequency when you do what? Not compress it. When you apply an electric charge, an AC charge, it causes vibration, okay? So these use vibration to do that. So torsional it produces a twisting motion. It's almost that same paddle wheel, but instead of spinning, now it's vibrating like this. It's kind of back, forth, back, forth, back, forth. And same thing. So now it has a known vibration. We send a known frequency into it. It's rocking back and forth at a certain speed. The thicker the fluid's going to slow down that vibration, right? A piezo crystal can also do it. I think you're getting at is that if you apply a vibration to it, or a movement to it, or pressure, it will produce a current. So you put electricity to it, it's motion. You put motion hitting it, it gives a current. And so you actually have like kind of an input, one that a piezoelectric crystal that's making this thing move torsionally, left, right. And then there's a second one hooked to it that motion is causing a current to feed back, a certain AC current to feed back. And we're looking at frequency of that return current. And the thicker the fluid, the more it's going to slow down that vibration. And so that return frequency may be different. And these typically are in the ultrasonic range. They're above 20,000 hertz, like 20 kilohertz or how. So say the input frequency is 30 kilohertz, 30,000 hertz. It vibrates 30,000 times a second. You put some fluid on there, a certain one fluid, a less dense fuel, maybe that slows it down to 29,000 hertz. That feedback ends up being 29,000 hertz. You put a more dense fluid in there, fluid that's colder fuel, a different grade of fuel that's more dense. Now maybe it slows it down to 28,000 hertz, that feedback signal, okay? Longitudinal does the same thing, except now instead of twisting a little thing, it's basically a little rod that vibrates up and down. And that's what we got here. So, or a wire, or like a wire type thing. So we have our known AC signal. In the piezoelectric generator, it's a crystal. It's got to be two different materials in crystalline form. That's what forms a piezoelectric crystal. Typically, it's quartz-based. Okay. Or they can be metallic crystals as well. There's a lot of different options there. But these are going to create a vibration that's going to vibrate this little wire or probe, and then the sensor side of it is going to pick up that vibration and send a signal back. And what it's looking for is this AC signal here is going to be a lower frequency when the fuel is more dense, when it's thicker, because it's going to damp the vibration in this connecting piece more than when the fuel is less dense, when the fuel is typically warmer. And so taking all those things into account, you know, the dielectric constant of the fuel, the density of the fuel, the level of the fuel, which we can convert to a volume because we know the 3D space that it's filling, that fuel quantity indicating system can convert that to pounds. Or, for those of you that are anywhere but the United States, it will convert it to kilograms. Okay, planes everywhere but the United States use kilograms. So that was when we did the when we did the computers. Did you see both of them had pounds like riveted to it? That was the result of an Air Canada crash that said you have to have the fuel units prominently displayed on your fueling computer because it was a case where the plane, let's see, 2.2 pounds per kilogram, right? Is that about the conversion? So they were expecting, you know, so 1 pound, 2.2 pounds per kilogram. So essentially a plane got fueled in pounds rather than kilograms, and roughly half the fuel it needed to make the flight. That happened a couple times, and then they said, you know what, we really should have it prominently displayed for the people fueling the plane what unit this plane is calibrated in, so they don't use the wrong one. Okay, but this system together can convert that to that volume. Okay. If our electronic fuel quantity system isn't working, we have our magnetic level indicator, and this works. You can see they look a lot like the drip sticks that you pulled out of the bottom of the 727 wing. But instead of being a tube, I mean, they might still be a tube, they don't have a hole at the bottom or anything. What they've got above this point is a magnet up here in the end. And so normally when you push this thing up into the wing, when it's locked in the stowed position, that float right here, this is a float with a magnet on the inside of it, that float is sitting at the top level of the fuel. And to get a level, you unlock, you know, it's got the little flat, you turn that, you unlock this, you pull it down, and they don't stick, you know, this O-ring here doesn't stick like those drip tubes do. They move pretty smooth. And as you're pulling it down, you can feel when it engages this magnet here, and you can feel the resistance to, you know, now you're trying to pull down on a float, and you'll feel that. So you can get it and then kind of get it where this is sitting at the surface of the fuel and get yourself a measurement without being shot by fuel coming out of the little hole at the bottom of the drip stick. Okay? So these are what you'll see on any pretty much modern aircraft, are these magnetic level indicators. You know, so here's, like I said, here it is stowed on the right, the magnetic rod's up. You unlock it, bring it down, the tip of the rod engages with the magnet, which sits at the fuel level and lets you know where it's at. Okay, they don't just put a float at the end. Why wouldn't they just put a float at the end of the rod? Why not just leave that sticking weight there and then just drop it down when you need it? What's that going to do? You know how a metronome works? You got this long fiberglass rod with a big weight on the end. Yeah, it'd sit there and do this all the time. It'd rock back and forth. It'd cause them to break off. So that's why you want that float to always be sitting supported by the fuel rather than being held on the very tip of the rod all the time. And they'll be at several points throughout the wing. Just like the drip sticks, there's going to be several points. So you want to typically find the most outboard one you can use that indicates some level of fuel. Okay. In all likelihood, if your outboard most one shows fuel, these two are going to be full here, right? The full, this one's at like half level, you would use your outboard one. Fuel drains down, now the top of the fuel is here and kind of go out, you know, this one's maybe half and that one's full, right? So you can use these to find it. So you work your way outboard to in. If there's one, if you have a center tank, typically they just have one, like what the 727 has with the drip sticks, just a single drip stick for the center tank, because it's not, you know, skinny and narrow and dihedral and all that. Okay. We've got the drip tubes still. You'll see these if you work on older aircraft. You all played with one of these already. No one shot each other too bad with them, I don't think. Right? You pull the tube down. When the top of the tube, fuel starts to, they call it a drip hole. It really more starts to shoot out of there if you're not careful, right? So, and you read the graduations typically at the bottom surface of the wing here. And then remember, the other thing you need to have is the pitch and roll attitude. And so we saw the one that's in the wheel well of the 727. Here's another plane that's also in the wheel well. Some they'll be back in the tail area. And we hang a plumb bob from a specified hanger point, and it points down to our plate that tells us our pitch and our roll. And then the part that we've been able to do, that I've been able to find charts, but not for the 727, is we use charts like this to convert that to a volume. Now again, we can convert to volume. We would have to, it's not going to give us a weight. And so you can see here, there's going to be a chart. You know, in this case, if pitch is 0 to 0.5 and roll is 0.25 to 0.5 degrees, you would use this chart. And then you look at the rod, which rod, right? And what it's reading and at what position. It gives you a volume in that tank. Now that gives us volume. Here it is, 0.75. So you'll have a chart for all kinds of, there's quite a few of these charts. There's charts for all different combinations of pitch and roll. Okay, left wing high, right wing high, nose high, nose low, you know, no, pitch negative means nose low, pitch positive means nose up, right? And so this gives us a volume. Is volume what we want though? No. Here's another one. Here's a bigger one, bigger chart, older chart. Okay. This left and right main tank, stick inches. This one doesn't have oh, right here. See, it says aircraft 0 pitch and roll. Fuel in pounds based on 6.7 pounds per gallon. So this one gives you pounds based on the average weight. Okay. So some of them are written this way. Some of them here are written in volume. If you have a volumetric one, what do you think you have to do? Convert. Okay. So one way is 6.7 pounds per gallon, but is it always 6.7 pounds per gallon? Now the other thing you would have with this is a hygrometer. Anyone ever use one of those? You fill a test tube. You did it in batteries. Do you ever check? Do you ever check the specific gravity of your lead acid? Right. You had a test tube. And you filled it with the battery acid, and then you put the little floaty thing in it. You can do the same thing with fuel. They make hygrometers for fuel as well. So you would have to take a fuel sample, and then you would have to do the little floaty thing to convert these to pounds. So that finishes up our level indication. Next, we're going to start looking at engine feed. How does fuel get from these tanks to our engines? And there's a couple different ways we can do it, but at the heart of the system, we're going to have some kind of a pump. The first ones I have here are electric pumps, and these are often called cartridge-style pumps. Most new aircraft are cartridge. This is not a cartridge. This is one you would install on the skin or in an access panel. It's an electric motor. Here's the intake is this screen, and outlet would be this little pipe right here. Some of them have intakes at the bottom here with a tube coming up and out. You can see this one's a 28 volt, so it's a DC pump motor. These are a centrifugal pump. You can see the pump itself is just this lower part right here. The impeller into the diffuser area and then up and out. Okay. Most new aircraft have gone to cartridge-style electric pumps. So there's a cartridge that's permanently installed in the aircraft right here. There's no pump inside of this. It's basically a housing. There's a spot for fuel inlet and outlet, and then the pump itself goes in from the outside. You push it in, turn it, and lock it in place. So they're easy to change without having. You don't have to empty the wing. You don't have to defuel them. You can pull these in and out. There is a check valve and stuff like that that's supposed to close. Okay. And so the way a lot of these work, they've got a handle on them. You raise the handle up. You turn the pump, and then you remove a drain plug, and it removes any fuel. When you turn the pump, it closes all the valves on the cartridge. You open that drain plug to drain whatever residual fuel is in the pump, and then you can pull the pump out and not get a big shower of fuel. To put it in, you have the drain plug installed, put your pump in, turn it, and typically push it up and throw the handle over. Okay. And you can see there's a cannon plug on the outside for power. And that's the other thing that we're going to is older pumps like this, you can see the fuel tube and the power. You know, on this one, it's on the outside. This one here, it's on the inside. They used to run power to these things through the inside of the fuel tank. Now, these wires would often be encased inside of metal tubing and all that, but still, if things aren't done carefully, it can turn into a TWA Flight 800 where you have a fuel tank that ignites. So newer planes, it's all run, the electrical is all external now. Okay. The fuel piping, the pipe comes off of here, goes into the fuel system, and then this boost pump cartridge plugs into that. Here's our intake and outlet. These are high flow pumps. Centrifugal pumps are high flow. They're gonna move a lot of fuel. They're relatively low pressure. When I say relatively low pressure, they might be 40, 50, 60 PSI, right? But that's relative compared to like a piston pump or a gear pump that can produce thousands of PSI. A piston type hydraulic pump or a gear type hydraulic pump is like 1,500, 3,000, 5,000 PSI. So these don't produce a ton of PSI, but they don't need to. They're just trying to move the fuel from the tanks to the engines. The actual injection, the fuel being injected into the combustion chamber, there's typically a gear pump on the engine that boosts that pressure and forces it in through those fuel nozzles. Okay, that's done by the engine-driven pump. But these are boost pumps out in the wing just to get fuel to the engine. Another way we can get fuel to the engine is using a ejector or motive flow or Venturi style pump. And that's what I've got pictured here. So these are often used as boost pumps. They can move fuel from the tanks to the engines. They're oftentimes used as scavenge pumps too. If there's like a low point in an outer bay, and for some reason the fuel can't flow, they'll stick one of these little Venturi pumps out in that bay to kind of suck the rest of the fuel into the inner bays or further inboard, or suck fuel and push it into the collector tanks. Okay. And so they look like, from the outside, they look like what's shown here. Inside, you have high pressure fuel has to come from somewhere. A jet of high pressure fuel is shot through a divergent duct that creates a low pressure, and that low pressure is going to suck fuel in from this port on the side here. And then this outlet here is connected to, you can see a fuel line going somewhere. Okay. That high pressure fuel, that low volume high pressure fuel, can come from a few different places. In this case, it says engine driven fuel pump. So if our electrical system stops working, if we don't have power to the plane, we absolutely, and this is part of Part 25 design, 14 CFR Part 25 design requirements, fuel must still make it to the engines even if we lose all our electrical systems and everything else on the plane. Okay? Even on wing-mounted planes, the collector tanks tend to be downhill from the engines. Now the engines are kind of downhill from the wing, and sometimes you can just straight gravity feed. Okay? But what we do is, remember that high pressure pump on the engine, most of that fuel is going to get sent in through the fuel nozzles into the combustion chamber, but we port a small amount of it off the engine, we run it back to the fuel tanks, and that's what provides the high motive flow pumps. And so even on the regional jets I worked on, where the engines are up on the tail, right? They are definitely above the fuel tanks. Once the engines were running, and those engine-driven pumps were sending high-pressure fuel back down to the Venturi pumps, those Venturi pumps, as long as the engines keep running, are going to be pumping fuel from the tanks up to the engines. To the point where we had a couple mechanics one night, brought a plane back to the hangar. They decided that the checklist was below them, did their shutdown as fast as they could. They were timing. They actually got out and said, hey, we got shut down in like 30 seconds. And those of us standing up to the ramp and said, hey, I think you forgot a couple things. And both engines were still running with the plane totally black. Now, parking brakes were set, and the engines were driving the hydraulics and keeping the parking brakes set. It wasn't going to go anywhere, but it's not good. That's not okay. But the whole point is that the engines and these fuel feed systems are designed to feed fuel to the engines no matter what. They turned off every single switch and whatnot in the cockpit. They turned the battery off. They turned the generators off. They turned, everything was dark. You walk in the plane, it was totally dark inside. The APU was shut down, and then you've got two engines that are still running, sitting there idling along, and they would continue to do that until the plane ran out of fuel, if you didn't go up and shut them down. So that's how these systems are designed. Again, they can also move fuel from one part of the tank to the other, and in that case, the way they work is they can also get this high pressure fuel from some kind of an electrically driven pump. So you might have an electrically driven, say you need to scavenge fuel using one of these from further out in the wings. You might have an electric pump in the collector tanks that's purpose is to send motive flow fuel out to the Venturi type scavenge pumps. So again, here you can see the jet of high fuel. Here's our high volume. Again, these are high volume, low pressure. We're not really worried about, we just need enough pressure to get it to the engine. High volume, low pressure, it's going to suck fuel in through the divergent duct. And you can see the divergent duct here and here. They get bigger as you go from left to right. So these pumps feed into our engine feed system. And here's a very, very simple, this is the same fuel feed system, just shown two different ways. You're going to draw a schematic of fuel feeds. You can draw a schematic that looks like this if you want. Or you can draw a schematic that looks like this if you're really artistic. I'll tell you right now, I cannot do this one. Okay? I'm doing good if I can draw squares, ovals, and some arrows. So that's all I expect out of you guys, unless you want to go more so. But maybe some color. I usually require color, right? Get colored pencils out, markers. But you can see here, this is a 3-tank setup. And we've got our center tank that's going to pump fuel out to the wing tanks. And then we've got a standby electric pump that pumps fuel to the, it says left main tank, but this is the collector portion of each tank, into the engine fuel feed. And here's that motive flow fuel coming back from the engine that runs those Venturi pumps, those motive flow pumps. And that's why they'll continue to run even if it's shut down. That same thing shown on this diagram. So from our center tank, we want to be able to pump fuel out. We got to get fuel out to our outboard tanks, and that's done. I'm looking at those backwards. There's the pickup here. Here we go. Transfer ejectors right here. These are going to pull fuel in and out to each tank. Okay. Here are those collector tanks that live in the center tank. Actually, let me go ahead because I think I got a bigger version. Yep. Here's the collector tank. So fuel from the wings goes into the collector tanks. And in the collector tank, you've got your left and right motor pumps, and you have a left and right ejector pump. And you can see the ejector pumps, the motive flow fuel for this whole thing, as well as a scavenge pump out here, is coming from the engines. So fuel is fed to the engines. Motive flow fuel comes from the engines. Okay. In a 2-tank aircraft, looks something like this. We eliminate that center tank. Here's our 2 collector tanks. Same diagram you saw earlier. Now we've got fuel aid on it. And again, we've got some AC motor pumps that feed fuel into the lines that feed the engines. And there is motive flow fuel coming back to run various motive flow pumps that will run the engines even if we lose electrical power. That's one way to look at it. That's the same fuel system, just a more simplified schematic that you would see. Okay. If you do have a bigger aircraft, here's an example of a 6-tank. It's got auxiliary tanks, 4 tanks for a 4-engine system. And all of these are set up, something I forgot to point out, is that you can see the right wing, primarily the right tanks are primarily feeding the right engine. And the left tank is primarily feeding the left tank. There's a cross-feed valve. Either side can feed either engine. But that would only be opened in the case where for some reason you've got an imbalance. You've got more fuel on one side than the other. You have this here as well. There's a cross-flow valve right here. You can also use this pump here to cross-flow fluid. That feeds the APU. Okay. 4-engine aircraft, 6 tanks. The main 1, main 2, main 3, main 4 are your primary fuel feeds. Fuel is pulled from the center tank and the horizontal stabilizer tank first. Once those are empty, that's used to, top off essentially the 4 tanks. The wings are divided into 4 instead of 2 tanks. And again, the number 1 tank feeds the number 1 engine. The number 2 tank feeds the number 2 engine. Number 3 tank feeds 3, and number 4 feeds 4. with the center and auxiliary tank basically moving fuel out to these other tanks. It goes out, and then these are the main pumps that feed, comes out into the tank area, and then from the tank area, it gets pumped up to the engines there. It can also be directly fed through this kind of a manifold too. So this is the 747. It's got a lot of different ways of moving fuel around. So that wraps up engine distribution.